Now, too, we investigate radiations in the invisible part of the electromagnetic spectrum in Science Topics.
But even more and more facilities will be added to them as the years go by.
Do you know, I can remember the days when you ate chips, and there we are, microchips.
A live radio broadcast.
Don't forget our phone in at 3:30. The number to ring if you would like to book a call now, 228-2255, whilst we listen to The Animals.
But how do the different sounds of the presenter's voice, the cassettes, records and tapes reach people listening to the programme? All these sounds are put through a mixing desk, and on leaving the studio, they're tested.
And he's abandoned in a park in the
But to be transmitted, they have to be changed. Why is that?
Well, the sound waves are audio waves at normal audio frequencies, but if you put those into a transmitter and try to radiate them, nothing would happen. They have to be mixed with another kind of wave, which is commonly known as a radio wave, and this is what happens inside the transmitter.
The transmitter receives the sounds from radio stations, usually by cables. At the transmitter, the main task is to add the radio waves, which will carry the sounds, so the output of the radio station can be transmitted from tall aerials over long distances. The radio waves move out, radiate from the aerial. As they travel through the air, the strength of the wave changes. It's stronger near the aerial, but gets weaker further away. But there are different kinds of radio waves.
The three common wavelengths or frequencies for radio in this country are long wave, medium wave, and VHF, which stands for very high frequency.
Long, medium and short or VHF radio waves can be distinguished by their wavelengths, and these wavelengths can vary enormously. A long radio wave can be 10,000 meters long. That's over 6 miles. Medium waves are between 1,000 and 100 meters long. VHF waves are only about 1 meter long. As with all waves, the shorter the wavelength, the higher the frequency. So a long wave is of low frequency, but very short waves have a high frequency, hence the name VHF. To transmit long-wave radio, you need a long aerial. All these lines are just one wire, carefully strung and supported. It's so long because the radio waves transmitted have a wavelength of 1,500 meters. So a medium-wave aerial doesn't need to be as long. Sometimes medium-wave aerials don't need a special mast to hold them up.
The main thing is to get the aerial as far as we can in the center of the area that we want to cover.
This church is to be used to suspend a medium-wave aerial for a temporary transmitter for the town of Bury. The aerial is just a copper wire, but its length and the height of the church have been carefully chosen to get the best medium-wave transmission.
The church steeple happens to be roughly the right height. It's about 50 meters. And what we've done, we've simply got a steeple jack to go up to the top, a job I wouldn't like doing, with a copper wire. He's attached the copper wire to the top of the steeple, and it's brought down to the ground to a firm anchor, and it's stretched. And then that bottom part is connected to the transmitter.
The aerial is tested before the actual transmitter is connected.
Right, okay, wait a minute.
The medium wave broadcasts will then radiate from the length of the aerial to be heard clearly by the people of Bury. But what about even shorter radio waves? What about VHF?
I suppose the main difference is the aerial itself. In the case of a VHF transmitter, the aerial isn't attached to the ground. The aerial is much higher up.
But VHF aerials aren't long wires, as VHF waves are only about a metre long. This mast doesn't transmit radio signals. It merely supports several VHF aerials, each about a metre long, and each radiating a VHF signal to a different area. All radio waves transmitted are monitored in the control room to ensure that they're of good enough quality to receive on a radio.
There's the market traders as well. There's good and bad in everything. But, I mean...
The different radio waves, long, medium and VHF, can then be selected and listened to. At Jodrell Bank in Cheshire, these huge dishes receive radio waves. But they aren't tuned into a radio station, they collect radio waves from space.
Radio astronomy is the study of the universe using radio waves instead of light waves. The optical telescope uses light waves to penetrate into the depths of space. We use radio waves for the same purpose. Our biggest dish here is 250 feet or 76 meters.
And this is the Mark I telescope. It helps to imagine that radio waves are coming from the sky all the time, and the larger the dish, the more radio waves it can collect. The oval-shaped Mark II dish receives shorter wavelengths than Mark I. In both dishes, the radio waves are concentrated to a focus point before they can be recorded. The telescopes can be steered to look at different parts of the sky. Over the years, important discoveries have been made about the Milky Way, quasars and pulsars. But do astronomers have any problems receiving particular wavelengths?
Well, on some of the wavelengths that we operate on, the very short wavelengths, these are sometimes called microwaves. We get a particular form of interference from such things as microwave ovens. If the oven isn't operating correctly, it can produce interference which can completely obliterate some of the radio signals that we're getting.
It seems odd that microwaves from defective ovens can affect radio telescopes. But in fact, microwaves and radio waves are part of a group of waves with similar electrical and magnetic properties called the electromagnetic spectrum. The wavelengths can range from 1 kilometre down to something smaller than an atom, but all electromagnetic waves travel at the same speed. Radio waves are the longest waves in the spectrum. Very short radio waves are sometimes called microwaves, but there's no break between one kind of wave and the next. They're all part of one continuous spectrum. Another important use of microwaves is for radar. Radar works by transmitting pulses of microwaves. Here, the pulses from the ground radar are reflected back off taxiing aeroplanes, and this echo can show the controllers the exact position of each plane. Radar is also used for military purposes. The bull nose of the Nimrod aircraft contains a radar aerial which transmits microwave pulses and receives echoes reflected off ships or submarines. The reflected signals are collected and displayed on screens which show the positions of objects in range. Shorter in wavelength than microwaves are electromagnetic waves called infrared or IR waves. These are given off by warm objects. We can't see the infrared radiation, but we can feel it as heat. Infrared is just a little longer in wavelength than waves we can see. We call these waves light. All the visible colours of light, from red to violet, are just a small part of the electromagnetic spectrum. Just shorter in wavelength than visible violet is ultraviolet, or UV. It's present in sunlight and is more penetrating than visible light. It's the ultraviolet which tans and burns us. Shorter still in wavelength are X-rays, and as the wavelength shortens, the penetration of the waves increases. UV can penetrate more than visible light, but X-rays can penetrate even more. X-rays can pass through the body's soft tissue to show the bones. This penetrating property of X-rays is used in hospital to detect broken bones. Angela has hurt her ankle. The X-ray machine will be used to see if it's severe. She has to be protected because X-rays can be damaging. The X-ray machine is adjusted so that the X-ray beam is just directed at the ankle and goes through to the photographic plate below. The X-ray pictures show the bones clearly and the break, which will need treatment. At the Manchester Museum, X-rays have been used on much older bodies, Egyptian mummies.
Have a look at this and see how the bandages are inside.
Okay.
Yes, they seem to be.
But why use X-rays?
X-rays were the most obvious choice of a tool for examination because, of course, they're totally non-destructive.
The mummies were taken to hospital and X-rayed with modern equipment. What can the experts learn?
We were able to learn a great deal about the mummies by using X-rays. First of all, you can see if there is actually a complete body inside the wrappings, because in some cases the ancient Egyptian undertakers lost arms or legs in the process, and they filled these in with sticks or stones, and this of course is not revealed until modern X-ray techniques. And then again, of course, very importantly, evidence of disease which remains in the skeleton or in any of the remaining soft tissues.
Has there been a mummy where X-ray examination has proved particularly useful?
Demetria is a very good example where X-rays can be used to good effect. The outer covering of Demetria is very beautifully decorated. It has a casing which in fact cannot be removed. So X-rays are really the only way of getting inside the wrappings to see what is hidden inside.
When the X-ray pictures of Demetria were taken, they showed there was a skeleton inside the case from which the experts were able to learn much more.
X-rays have also shown us a great deal about the dental health of the people. The Egyptians, once they reached adolescence, in most cases suffered severely from attrition, the wearing away of the outer surface of the teeth. And this was due to the diet. They ate over 30 kinds of bread, and grit would go into the bread in the making, and this would, of course, wear away the teeth.
The Egyptians also mummified children, and these too have been X-rayed. High doses of X-rays can destroy body cells of living people, so that's obviously not a problem with mummies.
Mummies are very good patients indeed. They remain still during the X-ray procedure, and of course you can take a large number of X-rays of one particular mummy.
Has it been interesting work?
it has been a fascinating project, and of course continues to be. We intend to go on indefinitely because the mummies can tell us a great deal about life and death in ancient Egypt.
Nowadays, hospitals are using another kind of electromagnetic wave. These are called gamma waves or gamma rays. But what are gamma rays?
Gamma rays are a form of electromagnetic radiation emitted from the nucleus of a radioactive atom. They tend to have energies rather higher than X-rays. In other words, we're right at the short wavelength end of the electromagnetic spectrum now.
Gamma rays are of shorter wavelength than X-rays, so are they used differently?
By and large, X-rays are very good at delineating anatomy. They can show you to very fine degree of detail the differences in density of different parts of the body. The nuclear medicine tests that we do with gamma ray emitters are detecting and determining function.
Gamma rays can be detected by this gamma camera. If a chemical which gives off gamma rays is absorbed by particular organs inside a patient, the camera will be able to detect the gamma rays given out. Here, the camera is being put into position for a test on kidney function.
Now, we're going to do a little test on you. It's going to take about half an hour, and I'm going to want you to sit here nice and still. Do you think you can do that?
Yes.
Okay, hop up on the chair. The patient will come into the department and sit down in a chair with the gamma camera behind him so that the gamma camera can see the two kidneys and the bladder, see, as it were, through the patient. The patient then receives this very small injection, and this comprises a very small quantity of a radioactive material that is emitting these gamma rays, which, after it's injected into the bloodstream, will be absorbed by the kidneys and will then pass through into the bladder. So he sits in front of the camera, and during all that time he's sitting there, the camera and the computer will acquire a sequence of pictures.
The pictures taken by the gamma camera are recorded. They can be punched up on the computer screen, which shows a picture of the two kidneys and the bladder below. The doctors can then study these results to help them find out if the kidneys are working normally. But high doses of gamma rays can kill cells, so isn't the treatment dangerous?
People often think of gamma rays and nuclear decay in a military context, but here this is entirely the opposite. We're using very, very safe materials. The purpose is purely for the safe and accurate diagnosis of a patient's condition.
Gamma rays, the shortest waves in the electromagnetic spectrum. As we've seen, the nature of the waves changes dramatically as the wavelength alters.